the only portion that was remaining, I mean, we talked about what is the brightness constancy assumption, how it leads you to an optical flow equation, which is kind of ill-posed, right? Because there are two quantities and there's only one equation. And then I showed you, right, what it means to compute a normal flow versus what it means to not being able to compute a parallel flow, which is what also gives rise to what is called the aperture problem. And I showed you some visual examples, right, where we ourselves got fooled, right, when we watch something through a small aperture, we're not able to make out the motion. And then we said that if we enlarge the aperture in the sense that consider a slightly larger neighborhood, then we should be able to solve it in a well-posed manner. And that's what we did, right? We sort of extended, we sort of took more points and introduced what is called a coherence constraint, spatial coherence constraint, which simply amounted to saying that the u and v's within a window are constant, right, for those set of pixels, and that's a reasonable assumption to make. And after that, we could come up with that's actually a method by Lucas Canade, and that just leads to a simple least squares kind of a solution where the eigenvalues have to be appropriate, and that's it, right? Then we said low texture, high texture, edges, what happens? Now, the only thing that is left is to kind of talk about large motion, right? I mean, if you remember, one of the things that we did in the Taylor series was to assume small motion, right? Both in in the spatial domain as well as in the temporal domain. Now, what can happen is there is a sudden motion, right, which is not smooth. Then in that case, you can have a big optical flow coming in. And therefore, directly using this method, it will lead to problems because underlying assumption is that the motion is small and all that. And when that happens, right, you can actually, there is a way around it. And we go back to a pyramid, right? I mean, if you're going to say recollect a pyramid structure that I talked about right in the beginning, right? I said that you can use estimates at a lower resolution to kind of build up your high resolution estimates. Exactly right, that's what is done. I'll just show you one sort of slide of that. Right, and then we will move on to the next topic. So if you look at this optical flow under large motion, right, this is what can happen. Let's see. Okay. So yeah, so what this means is that so what you do is you do something like a course to fine. So what this actually means is that if you this need not be a Gaussian pyramid. You can simply downsample. Okay, but the idea is that, right, you have the highest resolution here, but then you go down, right, in terms of the scale factor, right, you kind of make it into smaller versions of the original image. And as you know, right, if you had a translation of 5 pixels at some location in the high resolution, then when you go down by a factor of 2, right, it becomes 2.5. Then when you go down further by a factor of 2, it becomes 1.25 and so on. Therefore, right, when you are comparing images at a very low resolution, then this optical flow is going to be very small, right, between the two, which means that the assumption that we made right in the beginning is valid. And therefore, right, we can run Lucas Canade on this pair, get the estimate of the optical flow. Naturally, right, that's not the true optical flow because this is still at a very low resolution. Then you actually upsample it. You upsample the optical flow to the size of the next image, and then you also have to multiply the u and v by a factor of 2, because when you come up by that resolution up by 2, your displacements will also be twice the original, and then you warp this guy, right, with that kind of with that optical flow. And then the warped image is what you would compare with the other frame, and then okay, now again, because of the warping, right, your optical flow sort of difference is less, and again, right, you would compute an optical flow at that resolution, then use that, then upsample again and come. So by the time you come here, right, the warped version of this, which you're going to compare with this, is already quite close to this one. So the optical flow between this and this is much less as compared to what you started off with, right? So this warp, upsample, warp, upsample, warp, upsample, warp, right, is something that you have to continue doing until you hit the highest resolution. And at this point, if you compute the optical flow, then the expectation is that the warp guy will look almost like image 2. Okay, that's what you would do in a sort of a course to find, because you want to be able to use the Lucas Canade method even otherwise, right, even when there is large motion. And one of the simplest ways to do it is to actually go back to a pyramidal form that we had talked about at the beginning, and now you are finding an application of that, right? At that time, I just verbally said that you may want to use initial estimates coming from a lower resolution, right? Use that as initial estimate for the next resolution. and so on, right? I mean, here is a classic example of that. There are other problems also where you do that, but anyway, this fits right in our framework. Okay, this is the algorithm, multi-resolution as it's called, and you can see, right? So if you don't use a pyramid and directly apply the optical flow Lucas-Canaday method locally, of course, right, everywhere, then you see that, right, on the tree, ideally, right, where there is the largest motion, because the tree is very close to the camera, and therefore when there is a sudden motion, the motion of the tree is the highest, and the kind of optical flow vectors that you get, right, don't look really that good. This is because you are not kind of compensating for the optical flow, for the large optical flow. You're directly using the method as it is. If you kind of do the Lucas-Canaday with the pyramidal form, okay, then in that case, you get a much better estimate of the optical flow, right, in order to be able to tell what's happening, right. And then, okay, I'll just kind of leave you guys with this image that I showed yesterday, right. You can see that the image is actually still, there isn't nothing there, but then right, there is an illusion in your head that things are moving, right. This I want you to think about why this happens. Optical flow without motion. That means in your camera, right, in your own eyes, there is actually motion. Okay, there is optical flow, whereas the scene flow is zero. And if you have to take a picture with a camera, and suppose if you watch the adjacent frames, they would all look the same. But then your eye, right, your camera system, your kind of visual camera system is now sort of seeing an optical flow, right, when it is not there. Okay. Anyway, so we'll stop there. Okay. So as far as optical flow is concerned, and then we'll go to the right next topic, which is segmentation. Right. This is again a kind of mid-level task, and again as important as optical flow. And as I said, right, even optical flow can also be used to do this kind of an image segmentation task, right. I showed yesterday some examples where optical flow can actually be used for this, but right, in this talk, right, in this particular class, we'll kind of look at image segmentation the way it is kind of traditionally done if you had just one image, right. Optical flow will require a spatio-temporal sequence, right. Then you can actually predict the moving objects and so on. So that's one way you can apply optical flow for even finding moving objects. But now, right, we look at the case when you have to do segmentation given a single image.